Cool. Okay. We're getting off to a good start this time. I'm feeling good about today, right? Okay. So I wanted to start where we finished last time. And I think to get through everything, it might be a bit of a rush. So instead of doing any breakout rooms or taking times to work problems, I'm going to probably be talking more today. So let's give that a go. All right, so my pen was going in and out before, and it's in now. Okay, so last time I gave you, so far we've just been analyzing the single transistor amplifiers, the common gate, the common base, the common collector, common drain, common emitter, common source, finding R out, R in. We haven't done them all, but that would be good practice. And one of the main skills to take away from this class. So it's worth your time to go through the slides and do the small signal analysis to, again, find R in, R out, and gain. And then that technique, so we've been using that on amplifiers, but it can be used on any circuit you can come up with. If you're looking at how a change in voltage changes the current, or how a change in voltage changes a voltage, or how a change in current changes a voltage, or how a change in current changes a current. So the problem I gave you was this one. And I asked you if you put this in a box, so I couldn't see what was inside the box. And I said, okay, you have access to this terminal right here. How would you figure out what the resistance is? And experimentally, so there's two ways you can find it. You can find it experimentally, which is what you do in lab. You change the voltage and watch how much the current changed. So that's kind of it's observational. And then there's a theoretical, which is where we, theoretical. That's where we do small signal analysis, come up with an equation, put your current value in, and you get to see what the value is, what the resistance or the conductance or whatever it might be, or the current gain or the voltage gain. So for theoretical, for this one, we ended up with an equation, and I don't have it up right now, but we got an, darn pen. We got an R out. And the way we did this, we did small signal analysis, and we called this I out and this V out. Actually, let me redo that because it's not matching what I wrote last time. I test and V test. And then we did small signal analysis on this, and we got an RO plus a GM. Let's make this M2, M1, GM2, RO1, RO2, plus I think one of these was R1 and RO2, something like that. And then I had you say, okay, assume that GM is going to be some value like that, and assume your ROs for 1 milliamp, that could be 100K. And then if you did an approximation for this equation, what would you come up with? And the work for this is, even though I forgot to, what's that? Okay, even though I forgot to record at the beginning of last lecture, I recorded the second hour. So the derivation of this is in the second hour of video. Okay, so, and for this one, so this is going to be, so if this is 10 to the 5th, this is like 10 to the 10th divided by 10 or divided by 100. And these are just 10 to the 5th, 10 to the 5th. So this is going to be much bigger. And the approximation for this is that. And now this probably seems weird. The first thing we did in class was do a single transistor. And we had some voltage here. Remember, when we're doing R out, we would zero this. So it doesn't matter if this is V in or V bias. But we did a V test and an I test. And do you remember how big the resistance looked into the drain or into the collector? Do you remember how much how large that was? So let's don't want to redo work from last time, but for this one, we had, for the MOSFET, we had, just to remind you, so here's our single transistor, and we'd have V in on here. And now we're considering this the output. The source would be grounded, bulk's grounded. So again, I'm rushing through this. Ask me at another time if you have questions about this. But since this gets grounded, since we're looking at the V out here, this gets grounded, your VS goes to 0, and your VBS is 0. So your resistance for this circuit, for a single transistor looking at this node, don't know what's going on here. Your R out just becomes RO. Okay. So hopefully that looks familiar from last time. But now if you have something that has a resistance of RO and you put 2 of those in series, what do you expect to get? If you
RO 2?
Yeah, RO, not over 2, but times 2. I couldn't hear exactly what you said. But yeah, if you put 2 resistors in series, you should just get 2 RO. But because of these current sources, these voltage-dependent current sources, there's this eddy currents kind of get generated in here, and the feedback between these 2 transistors make for this to look like a resistor of actually RO squared, divided by 10 or divided by 100 because of the GM. But instead of adding the 2 ROs, it looks like RO squared. And this is really powerful. Okay. So the R out for this circuit right here is actually on the order of RO squared. And stacking transistors like that is called cascoding, or cascoded transistors, or cascoding. Okay, up to there's possibly a review. I know some of you weren't here, but are there any questions up to there? Okay, so let's see where cascoding might be useful. Remember, it's just stacking 2 of the same type of transistors. So if it's an NMOS, then it's stacked with another NMOS. If it's a PMOS, it's stacked with another PMOS. If it's a NPN, it's stacked with another NPN. If it's a PNP, then it's stacked with a PNP. So it's 2 of the same kind of transistors stacked on top of each other. Okay. There's 2 places you like large resistances. Can you think of 2 places you'd like large resistances?
The input of any amplifier.
That's one I didn't think of. Okay, there are 3 places you like large resistances. So your RN, we'll see another circuit that does good RN. How about, good call, by the way. Can you think of any place else you like large resistances? What's a large resistor mean?
Very little current.
Very little current, okay. And what happens when you change the voltage off on a large resistor?
It'll still be a low current.
The current doesn't change very much. So you like these on current sources. So far, we've been looking at just a plain old current mirror. Oh, come on, pin. This is even with new batteries. I don't know what's going on. Okay. So this was our current source. And this whole thing, let's put a green circle around it. This whole thing right here, that's equal to this symbol in schematic so far. So this is your current in, this is your current in. Turns out you can make a better current source. Remember, current source, the bigger the perceived resistance, the better current source it is. So you change the voltage, current's going to change less if it's a bigger resistor. So what you can do is, and NPN, so BJTs, MOSFETs, doesn't matter. This all works really well. So this doesn't change. There's a lot of ways to do the biasing. Let's come up with an equation for this. Now this right here, this is actually a superior current source. And that's because just as you did the math and saw it's a resistor of size, 10 to the 9th or something, 10 to the 8th, 10 to the 9th. That's what this behaves like. And that means it's just going to have a really constant current, even if the voltage at this node changes. It's still going to be an extremely constant current. And so these are also equivalent, but this current source is better than that current source. And we haven't done it yet, but can you think of a circuit from 307 where you used a current source, something in place of a current source actually, but something that served the function of a current source?
In an echo gate?
Exactly. So sometimes when you need a really nice echo gate or PECO gate or MCML gate, they use this as the current source. And you still need the biasing, so that's what's on the left here, something to set the base voltages or the gate voltages. Okay, so this one used the rule if R is large, then delta V doesn't change I. So that's using that rule. See if I can leave this on the screen for a minute. 3, is there some place that we can use kind of the inverse of the rule? So changing I, so current, changes. So if you have a big resistor and you change the current, what happens to the voltage across the resistor?
Hardly changes.
What's that?
It hardly changes also.
Think of your VDS versus IDS again.
There will be a huge change in voltage with little change in current.
Yeah, if you just change the current this much, you've gone from this point all the way out to that point. So the voltage had to change a lot.
Oh yeah, I see.
Yeah. Then this is, I know this plays with brains here, but changes V a lot. I have a friend that teaches elementary school, and she taught me about a lot being 2 words, and now I know it. So I'm proud of that. So, and where might that be useful? Got where this is useful when you want a constant current. When the current changes, the voltage changes a lot. Where might that be useful? Can you think of a place where you're throwing current across something to generate a voltage? What are we building in this class?
Amplifier.
Exactly. So how can, when you change the current across a resistor, where does that show up in an amplifier? That's a silly question. That's a weird question. But let's go back. Let's look at no pen. Still no pen. Okay. So if we have this circuit, could be a MOSFET or a BJT. I'm drawing it as a BJT. V out. Transistor generates the current. Current gets thrown across the resistor, and that makes V out move. So whatever current's going through there, V out actually equals VCC in this case, since it's a BJT, minus your I times your R. And if you change the current and this resistor is big, that's going to change your V out voltage a lot, and you'll have big gain. Mentioned a few times that this resistor, if you make it too big, your amplifier is just not going to work well. So we first replaced this. We said, okay, well, this can go up maybe 4K or 5K for a milliamp for a 5-volt drop. And then we said, okay, can we get something that behaves like a big resistor but doesn't have as big a drop? And come on, pen. It's too much to draw without a pen. Okay. So next bigger gain was and this is just some bias voltage here. Okay, and this one, did this have better gain?
Yes.
Yes, by a lot. And that's because this was behaving like a resistor of size RO. Just like up here when we, last time when we derived what size resistance this looks like at looking into the drain and the collector, both of them were RO. So right here, this is showing a collector to this node. So this is connected to the collector here. And we just showed last class that the collector looks like a resistor of size RO. And RO could be 100K or something. And that's just fine because this 100K, this is not acting like a resistor. It's in the traditional resistor sense. Like if you drew a graph of a regular resistor, it would start at the origin and go up. These resistors don't do that. If you look at the VDS versus IDS graph, this doesn't go through the origin. A regular resistor would be a graph something like this. This is behaving like a resistor because there's some change in current for some change in voltage, but it doesn't go through the origin. Okay, so that's great. All right, so how can you use cascoding to increase the gain even more?
The resistance of cascoding is, I don't know, generally that of a BJT.
Even more than a BJT. We haven't done the derivation for cascoding for a BJT yet, but it actually comes out to cascoded BJT. I was going to put it on the next homework. So I won't do the work here, but it actually comes out to, and this is it's putting two NPNs on top of each other, just like the MOSFETs. So it's this same circuit, except that's an NPN, that's an NPN. Okay, just on top of each other like that. It actually comes out to, again, GM of the second transistor times RO times R pi. I forget the subscripts on these. I'll look them up. Okay, but for a cascoded BJT, you still get a really large resistance. R pi might be 10K, might be 1K. So now you're multiplying 100K times 10K, or 1K. So R out for cascoded BJTs is also gigantic. So how can you use that to get even better gain? And you only, I'm sorry, I forgot to say one thing. Oh, my pen's back. This is just VCE SAT. As long as you have VCE SAT across this transistor, voltage from here to here, it will behave like that big a resistor. It just doesn't need that big voltage drop. So one more time, sorry, I keep repeating myself and then interrupting answers, but how can you use cascoded transistors to get even a bigger gain?
The change in V out will be larger, even larger.
Yes, yeah. Exactly. But where do the cascoded transistors go? And what do they look like? So if I started drawing from up here, what would I hit?
Probably so the two cascoded BJTs, and then right under that is the BJT that you're inputting the voltage into.
Okay, and then what are these BJTs? What kind of BJTs?
You said it was PNP.
Exactly, they have to be PNP. And they each have to have their own bias voltage, which means the biasing circuitry gets really complicated.
Professor, just understanding. So they have to be PNP because our bottom amplifier is an NPN, or are they just always PNPs?
The resistance that we calculated up here, we did it for a MOSFET, but it had to go into the drain or the collector.
Okay, got you.
So if you had NPNs up there, it would be going into the emitter. Okay. And that doesn't show you as big a resistance.
Gotcha.
Okay. So this is actually a lie, partly. This is actually much better gain than you got with this circuit. So it's a vast improvement, but you're not getting as much out of the circuit as you can. And to see, I'm not going to make you do the math, so feel relieved there. But I'm going to show you a shortcut now, so we can see why that's a slight lie. And to do that, I put a handout up on not Polylearn, Canvas. It's a Word document, and it looks like this. And we'll fill this table in Monday. But for today, I'd like to fill in a bunch of this table. Today, down to like right here, those 1, 2, 3, 4, 5, 6, 7 entries. And we did 2 last time. Which 2 did we do last time? the paint's a hint. So last time we looked at just a single transistor, and we looked at the resistance at this node. And we found that to be R out. So we can fill in 1 right there. So for the drain, it was RO. And I thought we did the collector too. Does anybody remember what the collector was? Okay. Actually, I think we just did it, didn't we? Or did we do that for MOSFETs? We did that for MOSFETs.
Was it the R pi plus RE? Is 1 plus.
That's different. That's the base resistance when there's degeneration. Ooh, I need to add that to the table. I'll fix up the table. Forgot to put that in. Darn it. Okay. Let's do in JT with degen. Okay, so I'll put that in right now. You said we found that looking into the base of a degenerated transistor, degenerated BJT, that gives you your R pi and then your RE times 1 plus. Okay, so if there's degeneration or you're doing a common collector, that's your Rn. So this is. Okay, what about a collector? Not coming back? Okay, so let's do that one real quick. Did the MOSFET just a second ago, but let's do this one too. So let's look at so if you want to try to figure out the impedance at a terminal, you treat it just like a small signal analysis problem. And the way you do that is you assume that all the other terminals have a fixed voltage on them. So this would be some V bias. If I wanted to find the perceived resistance here, I'd put a DC voltage on the other 2 terminals. Okay, and then I'd do small signal analysis just like I did before. So for small signal analysis, I see 1 transistor. So I do the R pi. I have my GM VBE. I have my RO. The emitter is grounded, and the base has a DC voltage on it, so I get to ground that. And then I'm trying to find how big the resistance looks at that node. So does anybody see any simplifications we can do?
Can get rid of the R pi because it's distorted?
Yeah, it's got a 0 volts here and 0 volts here, so no voltage across it, so that goes away.
That drops out the current source, right? Because VB is now 0.
That drops out the current source. And what you're left with is, and you're looking at that node, so what's the resistance you see?
RO.
Just RO. Okay, so we know for the collector, it's RO. Okay, what about for a MOSFET? What's the resistance on the gate? Infinite. So I think, do I have infinite here? Oh, darn it. Oh, that's right, I copied it off of someplace, but we'll just write infinite. Okay. How about This one's a little bit challenging. What if I give you like 1 minute here to try to work out what the resistance, the perceived resistance at the source is? And again, remember, if you're interested in what the resistance at the source, you put DC voltages on the other two terminals. And then you just go through small signal analysis like you've done before. So I'll give you 1 minute and see if you can figure out what that resistance is. Okay, not sure if that was enough time, but let's go through that. Okay, we're trying to figure out the resistance at the source. So we're trying to figure out the resistance here. And so we have a DC voltage here and a DC voltage here. And always for small signal analysis, draw out small signal model. And since there's a DC voltage on the gate, that gets grounded. And since this is also going, the drain is also connected to a DC source, that also gets grounded. And then your actual I test and V test are on that node. So did anybody see any simplifications that can be done here?
Both the current sources become the same thing, which is GM times negative V test.
You could do that, but you can make it even simpler. So that's a totally valid thing to do. But is there a way to make it even prettier?
I don't know.
So let's go through the rules. Number one is 0 DC sources. We did that. Number two is 0 volts across a resistor. No resistors with 0 volts across them, so that's gone. And then is VGS or VBS 0? Okay, let's see. VGS is 0 minus VN, so that's not 0. And then VBS is also 0 minus VN, so that's not 0 either, or I should say V test. So neither of those are 0. What's rule number 4? Anybody remember rule number 4? This is a quiet day.
When you treat the current source like 1 over GMX, like treat it like a resistor.
Yeah, and for that to be true, this voltage has to equal this voltage. So the question is, are those two voltages equal?
No. Oh, wait, yeah.
Yeah. They both share this node, so that node's already equal. And then you just have to check if these two nodes are equal. And if they are, then you get to replace that with the resistors. So this is nice. So this turns into 1 over GM. What about this current source? In this case, you're checking from the S is in common, well, what can I say? That is this voltage equal to this voltage?
Yeah.
Yeah, so as I don't remember who said it, but when you were looking at VBS here, you saw that that was the same as, yeah. Anyways, so VBS is 0 minus VTest, and the voltage across this is also 0 minus VTest. So this also goes to a resistor. This is kind of weird. It's upside down now, but there's your I test and your V test. So what's the R out here?
Just all of those in parallel.
All of those in parallel would be the unsimplified version. It's often good to do that first if you have any doubts.
It would be approximately RO.
The R is, which one's the biggest?
I do not remember.
RO.
Yeah, so this is right idea. The RO is really big. That might be like 100K. This might be like 10. And it turns out this is going to be 10 or 100 times bigger. So this might be, you know, like 1K or 100 ohms. So you have a 10 ohm resistor in parallel with a 100 ohm resistor in parallel with a 100K resistor. And what is this going to be approximately?
1 over GM then.
1 over GM, yeah. So you have to change your mindset to be an electron. And if you have 3 roads and one's really hard, you don't want to go. You're not going to want to go that way. So yeah, this approximates to 1 over GM. So that helps us fill in 1 over GM. Okay, not too much time left, but what do you think looking into the emitter? If I give you 1 minute to figure out what it looks like looking into the emitter? If I give you 50 seconds, no pressure. Okay, did anybody get an answer?
It ends up being like the same behavior, about the same behavior as the MOSFET, where one, you get like a resistor that's 1 over GM that's in parallel with RO, and that's approximately 1 over GM.
Perfect, yeah. So you might be noticing things kind of look alike here. The one thing that doesn't look alike is this base. And instead of spending time doing that calculation, anybody have a quick guess on what Rn might be for a BJT? Okay. If you ground all the other terminals, then you have the base going through R pi down to ground. And the Rn just looks like R pi here. So, okay. And then we already had GM, RO, 1, RO2. Okay, so we've got a list now, and now in 9 minutes, the why we did all this is let's do some problems here. Try to keep those visible. Oops. One thing I didn't say is anything that doesn't have degeneration. Let me add one more piece in here, and I know it's just kind of rushing now, but GM equals plus or minus. Do I have that on my plus or minus? No, I already moved that one out. Okay, so GM of any, we'll put an absolute value sign around it. GM of any single transistor amplifier, except for a common emitter with degeneration, or a common, anything with degeneration is just GM. Okay, that popped out of nowhere, so I'll slow down on Monday. But why, we just figured out our out values for all the terminals, and I just told you what GM is. What useful information can you get if you have R out and GM? Gain, exactly. So we have the resistances at the terminals, and we know what the GM is for most of our amplifiers. Let's do what I call the quick method, and I don't know if there's an actual name for it, but I needed to call it something, and so I just started calling it the quick method. That's a good portion of the homework. You say, what can I do in 7 minutes? I think you can all master the quick method in 7 minutes. Let's do a common emitter. And I think some of these are on the homework, so. All right, so when you do small signal analysis, when you do small signal analysis, you zero DC sources. So I'm going to take this circuit, and I see a DC source there, and I just zeroed it. Now that circuit won't work. If you actually make that a ground, that circuit won't work. But if you're doing small signal analysis, that's going to be a ground. Okay. So that's step one in the quick method. Zero all DC sources again. And then find all paths to ground. So let's see. If I'm on this output right here, how many paths to ground do you see?
2.
2. There's this one down to the actual ground. And where's the other one? Of course. It's up to that ground. Okay, so if you have 2 resistors both going to ground, what can you say about those 2 resistors? If you have 2,
parallel.
they're in parallel. Okay, so let's see. I'm going to try to figure out my R out here. So R out. So looking up, what resistance do I see? What kind of resistance do I see?
R.
R. And I know that's in parallel with the other path to ground. If I look down, what terminal of the transistor do I hit?
R.
Collector, and you go over here, collector, RO, and you're done. And then you say, does this have degeneration?
No.
Nope, so your GM is little gm. The only thing you have to think about is whether this is inverting or not inverting. And if it's inverting, you have a minus sign here. If it's not inverting, then you don't. So is this inverting or not inverting?
Inverting.
Inverting, so you have a minus sign, and then your AV, as it always will be, is your R out times your big GM. And that's with no small signal analysis, and this is the exact same answer you got when you did small signal analysis. Remember that some of these are approximations, like you said, it's 1 over GM in parallel with RO, so that changes a little bit, but really not all that much. So let's do kind of jumping ahead a little bit farther than, a little bit quicker than I planned, but since we're here, let's do this one just so no pen again. So let's look at our cascoded common emitter here. So we had V in. It'd be so much faster if I could use the pen. And this is V bias, VB1, VB2. Okay. What's the first step of quickMethod?
Ground DC.
Ground DC. So let's do that. And then we need to find R out. We're trying to find R out times big GM. Is there degeneration? We might as well do that first. Nope. So GM equals little GM. And on this one, it's actually a common emitter, just with this part changed. So do you think it's inverting or non-inverting? Inverting. Only the common base and the common collector are non-inverting. So if it's a common emitter anything, they just put a minus sign there and you're done. Okay. All right, so then we need to find R out. How many paths to, if we're finding R out, we sit ourselves on V out, and we say, how many paths to ground?
2.
2. Okay, I see one going this way. I see one going this way. What, if I go down, what terminal do I hit here?
Collector.
Collector, so I can go over here. What's the resistance of if you run into a collector?
RO.
RO. And that has to be in parallel, because if you have 2 paths to ground, that means the 2 resistors are in parallel. What's the resistance looking up? This is cascoded, so.
It's the resistance looking into the, I guess the collector of a PNP. I don't know how you translate that list to a PNP.
Okay, this is a special version. This is your cascoded. So it looks like you're looking into a collector, but these 2 transistors together actually form a cascoded transistor. And then your resistance actually goes up by a lot. That should be lowercase, RO squared.
So then it'd be the GM2 RO. Oh, I see. You just squared it.
Yes, I could put RO1. I guess that would be more correct. I shouldn't rush. Okay, and then you can see the gain is a lot bigger. I have 1 minute. I can do this. But you have RO squared in parallel with RO. What's that? What's your approximate R out then?
Is it just RO?
It's just RO, because you have like 10 to the 10th in parallel with 10 to the 5th. All the electrons are going to want to go 10 to the 5th. So this is actually approximately RO. So it did give you a good boost over this gain, but how could you make this, oh, I'm out of time. Last comment, how could I make this common emitter, how could I make this circuit have even more gain? Looking up, we have like RO squared, because the PNPs are cascoded, so they look like a giant resistor. But looking down, it's just RO. How could you make this? Where's the weak point there?
Maybe the resistance in the transistor on the bottom.
Exactly. So how could you improve that?
By increasing it.
By increasing it. And what's a good way? What's an easy way to increase your gain, increase your resistance.
If you use a cascoded transistor below.
Exactly. So if you cascode below also, I always go over with y'all. I'm sorry about that. So V in, and I'll put another V bias here. 3. And your GM is still going to be negative GM. What's your R out now?
RO squared.
RO squared in parallel with RO squared. So you have GM RO squared looking up in parallel with GM RO squared looking down, and you have a gigantic gain. Now your R out is on the order of on the order of RO squared instead of just RO. You just
Oh, does that
increased
mean
your
that?
gain.
Oh,
Oh.
sorry.
Go ahead. I'm sorry.
The transistor that you're biasing now on the bottom, is that also an NPN then? Whenever you're cascoding, same.
Yes. I'm sorry. Didn't draw that very well.
It's all good. Question: the gain that you had calculated for the BJT, like a little bit up, like the cascoded, you said AM2 times RO times R pi. So
For BJT. Thank you very much. Okay. What he said, I'm not sure who's talking, but yes, R pi. MOSFETs, it would be RO. BJTs, it's R pi. So I'm sorry.
No, it's all good.
I'm not very good at rushing.
Oh, okay. I wasn't sure estimating or like approximating that R pi and RO were the same or not.
No, what you said is right.
Okay, thank you.
And that's, believe me, it's much easier than doing the small signal analysis to find this result. But you get about the same result. Okay, more questions?
You said the first step is zeroing out DC sources. So why didn't we zero out V bias 1 and V bias 2?
They would be zeroed out. You're right. For this technique, you're looking for paths to 0, and there's maybe I should say that in a different way. Paths to the supplies. No, that's not a good way to say it either. You are finding the paths to 0, and these are, let me just keep it as paths to supplies, even though I don't like that answer. And I'll try to do better. Let me add that in. I'll change that. I'll try to come up with a better way to say that. But for these, you're really looking at from the output to the supply, not through the bias, not to the biasing circuitry, but I need a better way to say that.
So then for a cascoded transistor on your table, are we assuming that's for specifically the MOSFET then?
Yes. Thank you for correcting all my errors.
All right, cool. Thank you.
Once I get this all debugged, I'll repost. Thank you.
Yeah, thanks, Professor.
Okay, thanks.
Thank you.
All right.
Professor,
So for the common emitter one that you did, so the GM is negative because it's inverting. So the AV value would also be negative, even though.
Yes.
Okay, but you can write it like that, but then the actual value is a negative number.
Yes. GM's value is a negative GM. So when you replace this with, you'll get the minus sign when you replace big GM with little minus, with negative little GM.
Okay, that makes sense. Thank you, Professor.
Yeah. Any other questions?
Thank you, Professor.
All right. No, you were pointing to the right place every time. It's like, give me an answer when that stress is on. Okay. I think I'm gonna have to helmet it today.
Professor, I had a quick question on the homework.
Okay.
For circuit number 4 on question number 3,
Mm-hmm.
the Vn has the Vn plus and the Vn minus. How would we approach this?
Just look at, assume that since we haven't done diff pairs, assume that that node, the collector of Q10 doesn't move. So you can treat it as a virtual ground.
Okay.
So it's basically just that last circuit that we did, this Q2, Q4, Q6, Q8. Assume that's the last circuit that we looked at. Assume it's this, they're the same circuit.
Oh, okay. But this time with Vn at the base of 1.
Yes. Wait, say that again?
But like instead Vn is at the resistance we're looking for is at the base of Q8.
Yes.
Thank you.
Professor, I also have a question on the homework.
Okay.
For the design problem, it's asking for a V out that will make it a general purpose amplifier. I still don't really entirely understand what general purpose amplifier means or like what V out it needs. I just don't really understand that question.
Okay. So let's see if the pens come back. Nope. All right. So is it okay that with say a common emitter with passive load? Let me say that a different way. If you assume that you'll get the best gain when that is in the forward active region. So if you assume this amplifier will give you the best gain if it's biased in the forward active region, then you want to make sure that V out doesn't go down too far and put it into the linear region. Is that okay?
Yeah.
Okay, so the farthest V out can go down is VC sat. And the highest it can go is VCC. So as long as V out is between those two, VCC. As long as V out's between those two, then you're going to get good gain. Okay. When I say general purpose, what I mean is that you don't know how the end user is going to use your amplifier, and they might need. You don't know if your output's going to have to go up or down. So the safest place to put your V out before you get a signal is right in the middle. So right between these two values.
Okay, that makes sense. Thank you.
Okay. Right. I got to helmet it, y'all. My ears complaining. it's already time. Hi, everybody. We've got 9 people today. So let's see. I don't think there was any. I don't think there was any business that we had to go over. I think somebody mentioned something in the first section, but can't remember what it was. Does anybody here have any business needs to be discussed? Nope. Okay. Then, just to, you guys are getting good service here because we usually get to the end and then get to discuss that more stuff than the first section. But let's see. I put a handout on Canvas. Whoops, all the answers are in on my picture. I should hide those. And the table that we're going to fill out today on the homework, if you notice, there's the quick method. And of course, you can tell that I named that because it's a really silly name. But I needed to have some name that separates it from doing small signal analysis to find gain, R in and R out. So that is where we're going today. We're trying to figure out how to do the quick method. And the quick method, again, is just, it means you don't have to do small signal analysis, and you can just look at a circuit and say, oh, I know what the gain of that is, or, oh, that has a big R out, so it's going to load easily. Oh, it has a small R out, so it's going to be difficult to load. Or that has a big R in, so it's not going to load other circuits. So is that okay, our goal? Figure out the quick method? Okay, then I drew all of this in the first section, so it took quite a bit longer, but I think I'm in a point. Last time, the last circuit we looked at was a cascoded MOSFET. And cascoding means you have 2 of the same kind of transistors. So if it's a MOSFET, I don't mean that it's 2 MOSFETs. I mean it's 2 NMOS. It has to be the same N or P. So right here I've got 2 NMOS stacked on top of each other. And think you went through the math and you looked at this node right here. And that is, we put it in a imaginary box here, and we said, okay, figure out what resistance it looks like at that node. And there's 2 ways to do it. There's the doing it experimentally, and that could be LT Spice, or it could be in the lab. That's a totally valid way to find those values. In this class, we're trying to concentrate on the theoretical, so that would be, doing small signal analysis to come up with the equation for the resistance at that node. Okay, and last time we went through the math and we got an equation. I might have, no, I think these subscripts are okay. So we got an equation something like this. And at the very end, I rushed a little bit and said, if you assume RO's like 100K, and then you assumed GM was maybe 1/100th to 1/10th, somewhere in that range. They can go smaller or they can go bigger, but let's say in general, say GM's between those 2 values, then which of these 3 terms is going to be the biggest?
The center term.
The center term. And this is going to be like, if this is 10 to the 5th, this is going to be 10 to the 10th, maybe divided by 10 or maybe 100. And these are just going to be 10 to the 5th. So this term is definitely going to be bigger. So for MOSFETs, if you cascode and you look at this node right here, it looks like a resistor of something on the order of 10 to the 5th. Okay. What do you think the minimum voltage you can have at this node? Remember, if you had an actual resistor that was 10 to the 5th and you had a a milliamp going through it, you'd need 100 volts across it. But the advantage of using a transistor that behaves like a resistor, in other words, the delta V over delta I, behaves like that resistor, that doesn't say anything about the actual voltage across it. It just tells you how much V changes when I changes, or how much I changes when V changes. So what is the minimum voltage you could have here and still have it act like a resistor of this size? You want the transistors to be in the forward active region, or saturation for these MOSFETs. What's the minimum voltage you can have here and keep M1 in saturation? Kind of a generic term for it.
VC sat.
VD sat. Okay, and then what's the minimum this could be and still have it in the saturation region? Have M2 also in the saturation region?
Would it have to be 2 VD sat?
Yeah, 2 VD sat. So you could have like 0.2 volts across this and have this behaving like a mega ohm resistor. It's kind of a neat trick. Any question up to there? Okay, and then for the other class, I think there were a number of people that weren't there last time, and nobody answered when I asked what the perceived resistance was for a single transistor on the drain or the collector. So for that, just because we're going to be, where do I want to go next with this? Yeah, so we're going to be filling in that table. Actually, let me do something here. Let's do, I have all the answers in there, but okay. So for the cascoded MOSFET, were you all here? Did you go through the derivation of this equation, or did you see the video? Okay. Anybody not raising their hand? Okay, so we'll assume that this equation, whether you watched the video from class or whether you were here for that class, you're okay with this derivation. Okay, so what we're going to do here is we're going to use this in a minute, but we're going to use this in a minute, but let's look at this cascoded one. It's on the order of RO squared. Yeah, it's divided by 10 or 100, but it's on the order of RO squared. If you're finding the R at this node, you do the same thing you do for small signal analysis, but if you have a single transistor and you want to see what the perceived resistance is at each terminal, you set the other two terminals to DC sources. So if you're trying to find the collector or the drain, you set the base and the emitter, or the gate and the source, to DC voltages, and then you just do small signal analysis. So in this case, if you were looking for this node, for the drain, then we'd write the small signal model just like you do for small signal analysis. And then you say, well, I'm interested in what's happening at the drain, so I'm going to set the gate and the source equal to DC voltages, which just turn into grounds. And then I'm going to do the analysis and try to come up with the result. I'm going kind of fast here, so anybody that has a question, please interrupt, because everyone's shy with the pictures. On the CPE faculty meeting, I just used a picture and then I went and ran on the treadmill for half an hour. But yeah, since I can't see anybody's faces, I can't really tell what's going, whether you've got it or not. But yeah, so if you ground this and ground this, then you see that VGS is 0, so this current source goes away. If you grounded the source, so VBS is also 0, that goes away, and all that's left is RO. And that's how you can tell that the resistance at the drain is perceived as RO. Any questions up to there? Okay, so my first challenge to you, actually, I think we did, this was for MOSFET. Do you remember what the collector resistance is for a BJT? So having seen this work right here, I'll give you 1 minute.
It's just R naught, isn't it?
Yes, it's just R naught. Okay, so let's put that in our table. So we had we just did a cascoded MOSFET. So that's GM, RO, RO. And we just did the drain, which was RO. Just did, last time we did the collector also, that was RO. Okay. What do you think the resistance looking into the gate is? You don't need to do small signal analysis for that. You can.
Wouldn't it be infinite?
Infinite. Okay. So next challenge, and I'll let you work this out. I'll give you 2 minutes. Next space in the table there is figuring out the source resistance. Remember, if you're interested in the source, you assume that there's DC voltages on the other terminal and you do small signal analysis. So see, let's put up the, I'm not sharing, am I? I wasn't sharing at all, was I?
No, you've been sharing.
Oh.
You've been sharing the tables and stuff.
Oh, okay. Okay, good. This is weird. Sometimes I get a green square around it, and sometimes I don't. Now I can see I'm sharing. Okay. So your challenge is to figure out the source resistance. So if the other two terminals have DC voltages on them, try small signal analysis to figure out what the source resistance looks like.
Would it not just be the inverse?
Okay, do small signal analysis to figure it out as practice. It's good practice. Okay. What'd you all get?
Would it be 1 over GM in parallel with 1 over GMB in parallel with RO.
Very nice, yes. So that's RO parallel 1 over GM parallel 1 over GMB. And let me just go through it real quick. So since you treat this exactly like a small signal analysis problem, I see a transistor. So first thing I do is convert the transistor into the small signal model. And then I connect things up as I saw here. And the gate is connected to a DC source, so that goes to ground. The drain is also connected to a DC source, so that goes to ground. And right here, and the value we're trying to find is R, which is V test over I test. And there's no V into 0, so nothing to set there. And always forget to draw that. Okay, so how did you get your 1 over GM?
You have VGS across GM times VGS.
Okay. So you want to see if the green plus minus equals the red plus minus, and does it? Yes. So the minus is on the same terminal, so that's equal to each other. So you just really have to see if that node voltage equals this node voltage, and they're both ground. So you do. So this goes to a resistor of 1 over GM. What about this? There's VBS there, and then there's the voltage across the current source. The minus here is in the same node, so that's the same voltage. So you just have to figure out if this is the same voltage as that, and is it? Yes, they're both ground. So the voltage across the current source equals the voltage in the equation in both of these cases. So you can do that. Whoops. 1 over GMB. And the RO is still there. So you have RO. And this is grounded. So it's kind of like the resistor is upside down. V test. And your I test. And you can see it's all three of those in parallel. And let's introduce some rules. RO is much bigger than 1 over GM, and GM is much bigger than GMB. So GMB is like a 10th or 100th of GM in most cases. So if GMB is much smaller, what's going to be bigger, 1 over GMB or 1 over GM? If GMB is smaller.
1 over GM.
Okay. I asked that in a really weird way. So if GMB is much smaller than GM, is 1 over GM bigger or smaller than 1 over GMB?
Smaller.
Smaller. Okay. So if this is smaller than both of these, then what's this approximate to?
One over GM.
1 over GM. So the resistance looking into the source, you can go back to our table here, is 1 over GM. Okay, so we're getting through this table. What about the resistance looking into the emitter? So if you have a single BJT and you want to see what the perceived resistance looking into the emitter is, put DC voltages on the other two terminals. What do you think you get? Let's give you 1 minute. Okay, how'd that go?
Isn't it R pi plus 1 plus beta times RE? Oh, wait. Never mind. We don't have an RE. Just kidding.
It's actually friendlier. Yeah, it's friendlier than when there's degeneration.
Like just R pi.
Let's do the work again. So if you have, yay, my pen's back. I'm so happy when my pen actually writes. Oh, whoops, that's not what I want to do. So this is going to be my V test and my I test. And I just assume there's voltages on here that's going to put it in the right region of operation. Okay, and then just like with any small signal analysis, I draw I see a transistor here, so I need to replace the transistor with a small signal model. And then I see that the input is over here. It's on the emitter. I see that there's a DC voltage into the base, so that gets grounded. I see there's a DC voltage on the collector, so that gets grounded. Then, do you see anything you can make pretty?
The dependent current source can be modeled as a resistor.
Exactly. So again, you want to see if that voltage equals that voltage, and they're on the minus is on the same terminal, so you know that voltage is the same. So it's just checking to see if these two voltages are the same, and are they? Yes, they're both ground. So you can rewrite this as I test the test. And that's going to go into, we have an R pi going to ground, and we have a 1 over GM going to ground, and RO going to ground. So what's your R?
All of those in parallel.
And then you know what's coming next, right?
You can approximate it as 1 over GM.
Yep. And that's a fair approximation. R pi, if it's 1K or 10K, RO 100K, it's not going to be, they're going to be very large compared to 1 over GM. So got that. Emitter 1 over GM again. So what's left is the base and then a couple of others. So what about the base? What's the resistance looking into the base? And you're about 10 minutes ahead of the other class still. And again, when you're looking for the resistance at the base, you put DC voltages on the other two terminals and then just do small signal analysis. Anybody get an answer?
I'm thinking it's just R pi, but I'm.
Yep.
Okay.
So let's do it real quick since we're so far ahead. We've got our transistor And we're trying to find the resistance here, so you assume voltages on these two terminals that put it in the forward active region. Same steps, your R pi. This is grounded. This is grounded. This is your I test, V test, and this is horrible overkill because as soon as I drew a ground on this node, it doesn't matter what's on this side at all. This resistor is going straight down to ground, so this side can do whatever it pleases, and it doesn't change the resistance on the base. Okay, and R equals R pi. Okay, almost there. Oops, what happened to this? So that's R pi. Okay, anybody remember what we won't derive it right now, but anybody remember what the Rn is when there's degeneration or it's a common collector?
Isn't that one R pi plus 1 plus beta times RE?
Yes. Okay, we'll cover these two Monday, I guess. For the cascoded BJT, we haven't worked that out. I wanted to put it on the next homework for practice for you. So this one, I'll just tell you, it's GM ROR pi. And we have our table finished. Yay! Okay. It's one thing I forgot to talk about, but we'll move that to the end. So let's see how we use this. And again, our whole goal is to use this quick method, which means you don't have to do small signal analysis. You can just look at a circuit and say, ah, I know what that Rn is. Oh, I know what that gain is. Okay. Let's do got our table here. Let's start out with, yeah, there's two things I forgot to do. Okay, I guess we're not as far ahead as I thought, but so this is your common emitter. And the way you do the quick method, the first step is to zero sources. So let's see if this will work. And this is, I should say supplies. Let me say supplies instead. So, so here's a supply. So I'm going to zero it. And this supply is already ground. So it's zeroed. And now if second step here is I realize that gain. Do you remember? Well, I'll just write it out. Does this look familiar? Okay. So gain is big GM times big R out. So if you could find these two, then you could just multiply them, and then you'd have your gain. Okay. A rule for big GM. Big GM, absolute value of big GM equals GM unless there's degeneration.
I might be confused. Shouldn't that absolute value be on the little GM?
No.
Okay.
This is so. If you have, is a common emitter, is it inverting or non-inverting?
It's inverting.
Inverting. So if it's a common emitter, it's the only one where this happens because common collectors and common bases are non-inverting.
Okay.
For a common emitter, big GM equals negative little gm.
Okay. Oh, okay.
But for a common collector or common base, when I should say common source or common emitter, you should add common gate, you should add common drain, then big GM just equals little gm with no minus sign.
Okay. Thank you.
Okay. So, so now we've got these two terminals grounded, and first let's find R out. I feel like making this bigger again. Let's find R out first. So the way you find R out is you find V out, and then you see how many paths to ground you see. So if I'm at V out, how many paths to ground do you see?
2.
2. So I see 1 to the actual ground. Then where's the other one? Since we just made it ground.
Going up.
Going up.
Yeah.
Yes. So there's 2 paths to ground. And the circuit, when I added a ground up here, it made this circuit nonsense. I mean, it won't do anything if that was an actual ground. But if we're doing small signal analysis, we would ground that node. Okay. So now our challenge is to find R out. And if you notice, I have 2 paths to ground. So I basically have 2 resistors in parallel. So if I can find the resistance going up and I can find the resistance going down, I can just put them in parallel to find the resistance that you see on the output. So looking up, what resistance do I see? Whoops. So looking up, what resistance do I see?
R.
R. You're going through a resistor size R, that's what you see. Real resistors have the same, are the same whether you're looking at them as small signal resistances or actual resistors. Okay, and that's 1 path to ground, and we have another path to ground, so that'll be in parallel. So I come in here, and what terminal did I hit here?
The collector.
The collector. So if we go over here, let me move this over. Maybe I can. Pretty close. For the collector, what's the resistance you see if you're looking into a collector?
R naught.
R naught. You're done. Okay, and then there's it's a common emitter. You still need GM to find gain. Remember, gain is GM times R out. So you need to find GM. What's GM for the circuit? Is there degeneration?
No.
No, so you don't have to worry about a special case. And so you know it's a GM. And then you just have to figure out if it's a minus or a plus.
It's a minus.
It's a minus. And then your AV is just your big GM times your big R out, and you're done. You have the gain. What about if I asked you what the R in of the circuit was? What terminal do you hit?
The base.
Base. And what's the R when you look at a base?
R pi.
R pi. And no small signal analysis needed. Okay. So let's, I think we're still doing fine. I have a couple more things just to make sure you have the same information as the other class. Let me give you another one of these problems, and I know it's on the homework, but so that's the gain. Let's see, let's mark this down. So for a common emitter with a passive load, this your gain is minus GM times R in parallel with RO. And the R out, what can you generally approximate the R out of a passive load? What can you approximate this as, usually?
Or not.
Is it R naught?
Yeah.
It's R.
R. Remember, all
Oh,
the,
it's smaller. My bad. Yeah. Yeah. It's
yeah, electrons like to go the easy path. So the gain here is minus GM times R, approximately. So let me go to the next circuit. Oops. Go to the next circuit. Let me give you candidate number 2. So what kind of amplifier is this?
a common emitter with active load.
Common emitter with active load. Okay. And let's do the same thing. What's the first step of the quick method?
What are we finding?
R out, sorry. Well,
Oh, I guess that doesn't, yeah, ground the sources.
ground the sources. So that goes to ground. And now, how many paths to ground do we have?
3.
Okay. For this, don't consider that a ground, just consider the sources as grounds. Which I'm going to come back and try to figure out because somebody in the first class asked me that too, and I couldn't answer. Okay, so now let's find R out. So we have 2 paths to ground. We have one going to the actual ground. And again, if you in this circuit, if you made that ground and tried to run the circuit, it wouldn't run. It's just because when you do small signal analysis, you ground the DC sources. So on this R out, let's say we go down first. What terminal do I hit?
Collector.
Okay. And then for the collector, what resistance do you see if you look into a collector?
RO.
RO. And that's in parallel with the other path to ground. If you go up, what terminal do you hit?
A collector.
Collector. And what's the resistance?
RO.
RO. And you're done. Still have to find GM. What's GM? Is there degeneration?
No.
Okay, so GM is just going to be a little GM. Is it a plus or a minus?
A minus.
Minus. It's still a common emitter, and common emitters are inverting, so you have that. Okay, so your AV equals your R out, equals your GM times your R out. And if the ROs are approximately the same, what's RO in parallel with RO?
RO over 2.
RO over 2. So this is only true if the ROs are about the same. Okay, so I claim that you had a gain of minus GM times R before. I think we've probably increased it quite a bit. We've gone from maybe 5K to 10 or 100K. So you've got a good increase in gain. And that was by making this look like a bigger resistor. So can you think of another way to any, how can I say this, just something that looks like even a bigger resistor?
Hey, Tina, I had a question.
Okay.
For the common emitter with active load, how would you find the Rn value?
Okay, Rn, it's hitting a base.
Okay.
And as long as there's no degeneration, Rn is just R pi.
Okay.
If there is degeneration, then you have that R pi plus RE times 1 plus beta.
Okay. All right. Thank you.
Okay. So can anybody think of another way to increase resistance? Hmm?
Do you mean for RN?
For so if you're trying to get a bigger gain, I'm talking about this one.
Could you cascode PNPs?
Yes. Okay. So I'm gonna have to scroll down here. So if you cascode the PNPs, and we'll just call that V bias 1, V bias 2, and our input here, and V out. Okay. Then first step of finding gain using the quick method.
Ground it.
Ground it. And now there's 2 paths to ground. R out, I should make it. So there's this path to ground. What's this path to ground look like?
RO.
RO. You hit the collector, and if you go back over here and look on this table, that's RO. And you have 2 paths to ground, so they're in parallel. What about looking up?
GM RO times RO.
GM RO. And these are BJTs, so that the amount of resistance is a little bit smaller. It's the RO.
Oh, sorry,
R pi.
yeah.
That's the only, yeah. Okay. And then you need GM.
Still negative little GM.
Negative little GM. So this is still a common emitter. It just had its load replaced with the cascode. So it's still a common emitter, so it's still minus GM. Okay. If you look at this, what's your R out equal approximately? Let's say R pi is 10,000, RO's 100,000, GM's 1/10 or something.
Would it just look like RO?
Yes. So, for all that extra work, you only got an increase of 2 in your gain from the active load. But there's a trick. There's a way to get a stupendous amount of gain. If you notice, the problem here is you're putting something, it's really big, but it's smaller than this side. How could you? Oh, go ahead. Go ahead. You're probably answering the question.
What if you cascode the NPNs as well?
Exactly. Yes. So this might take a minute. 1 PNP, 2 PNPs, and then we hit the NPNs. 1 NPN, 2 NPNs. You have your V in, you have your V bias 1, V bias 2, V bias 3, and your V out. I think I accidentally did most of the homework, but okay. Let's do GM. Is there any degeneration? Nope. So it's just little GM, and then you have to figure out if it's a minus or a plus. This is still a common emitter. So it's still minus. And now we have to figure out R out. What's R out?
GM RO R pi.
GM RO R pi.
Over 2.
Over 2. So you have GM RO R pi going up and GM RO R pi looking down. So those get put into parallel. And if they're about the same size, you get that. Now your gain Still minus GM out front, so nothing's changed there. And now, even though if you assume R pi is 10,000 and GM is 1/10 or 1/100th, now you've got a sizable gain improvement over your just cascoding on one side. So questions there? There's one more thing I wanted to say, but I'm gonna go over time if I do. I'll try, but any questions on this and what the quick method is?
I'm fine with the gain calculation and stuff like that,
Okay.
but I'm a little confused by earlier you said Rn for I think the active load is just R pi.
Mhm.
Why don't we look at the line going up as well?
Okay, so let's take that off to the side here. So if you have the active load, pen stop working again. So you've got your active load, right? Or passive load. If you, sorry for the lousy picture here. You've got your V in and your V out. If you draw that small signal model here, you get your R pi and the emitter gets grounded. So it actually doesn't matter what's happening in all of the rest of the circuit.
Oh, okay. Oh, that makes sense. Okay.
No. The only time that this node gets altered is if there's degeneration. So if there's no degeneration, just R pi and you're done.
Okay, thank you. That makes sense.
Okay. Let me try to do this last topic. I have, what, 1 minute? I have 55 seconds. I can't make it, but so cascoding, that's pretty neat. You just put two transistors on top of each other, and each one, if you look at the collector or the drain, it looks like RO. So if you put two in series, you'd think it was 2 RO. You put resistors in series, and it should just double the resistance. But what happens is there's some like eddy currents, and those dependent current sources kind of work with each other, and that's where you get the basically RO squared or the R pi RO. So that's why the resistance just blows up. Okay, so that's great in gain. You saw how it could increase the gain of a common emitter drastically. But where else do you like large ROs? Can you think of any place else you like large resistances?
For your input?
Okay, actually, there's 3 places. I did that in the last class too. Yeah, how about other than that? If you have a large resistance and you change the voltage across it, what happens to the current?
Doesn't change much.
Yes, so what's that acting like?
A current source?
Exactly. So the current source that we've seen so far is actually one of the worst current sources there is. Resistors are the worst. Current mirrors are the second. If you cascode, remember this looked like, when it was just a single transistor, this looked like RO. Now it looks like RO R pi times GM. And what that means is saying, oh, this looks like it has a big R, that just means the current doesn't change very much even if you change that voltage. So the bigger the resistance, the better the current source. So cascoding gives you a great current source. And we'll look at that a little bit more. The rest of what I told them was about, you know, what we saw with the cascoding the load. But current sources, anytime you can increase the perceived resistance, You just made it a better current source, and that's why cascoding is used. Any place you need a really good current source. Can you think of? Oh, go ahead. Go ahead.
So does the more transistors that you cascode, the better the current source it becomes?
Yes.
Or it's too good?
No, you can, if you work it out, I did it a long time ago and I haven't been brave enough to do it since, but I stacked 3 transistors and tried to do the small signal analysis and I got an RO cubed for MOSFETs. So yeah, it looks like it goes up a power each time. I'm not sure. I only was brave enough to try it up to 3 transistors. So.
Thank you.
Okay. Can you think of a circuit that used a current source in 307 and 347?
Echo.
Yeah, exactly. So sometimes you see those at the bottom of the ECLs or PECLs or MCMLs. Okay, somehow managed to cram all of that information in. Are there any questions on a quick method or no? You're good? Okay. I would offer to stay. I have a thesis defense and I haven't read the thesis yet. I have it in half an hour. So I should probably go do that.
Good luck with that.
Good luck.
Yeah,
Have a good
thank
weekend,
you.
Tina.
All right. I'm available if you have more questions later, though. Yeah.
Bye, Professor.
Bye-bye.